Hello everyone. We are continuing with kinematics and motion in a straight line. In the previous class, what we had discussed is derivatives and their use in obtaining the instantaneous values. Now, what kind of instantaneous values are we talking about? Instantaneous speed or instantaneous acceleration, and we had done some numericals. We had solved a few examples related to it, right? Those examples were in the form of numericals, of course, and these numericals but what is the physical significance? Although we had obtained the numericals, but we want to just get into the physics of it. What physics do we get from it? Although we've obtained instantaneous speed or velocity as well as instantaneous acceleration, so you can say that we have already obtained the physics of it, isn't it? But still we can predict the behavior of an object in motion. Okay, this is what we are going to discuss now. What kind of behavior am I speaking about in this case? Now, the behavior as in its physical state related to its kinematics, means if it is moving, how is it moving? All we can predict that, okay, by just looking at the equation. It will be very easy to predict now, since we have understood. Now, to understand clearly about the behavior of a given object in motion, we can consider the following cases. I'll just give you two cases in which you can understand what I'm speaking about, and you can also predict as well. So suppose an equation is given as s is equal to k times of t, where k is a constant, s is the position or the distance that is related to time, s is equal to k into t. Now we have to find the instantaneous speed, suppose, in this case. Then what do? We just take the derivative, that is the instantaneous speed is equal to d by dt of s, right? The position that is given over there is equal to d by dt of the, we substitute the value of s, that is k into t, that is given in the equation, right? So k is the constant, it goes outside. As per the rule of derivative, it cannot be differentiated. So dt by dt is equal to 1, so we are left with k, which is a constant. Now the instantaneous speed over here, as you can see, has become a constant. Okay, that means it remains the same throughout. Its value does not change. Yes, it remains constant, and it remains constant at all instants of time, because instantaneous speeds equation has been obtained to be a constant, so it will be remaining constant at all instant of time. And that happens in this case, that is s is equal to some constant times of t, that is the first power of t, when the power of t is just 1. Okay, first order. So s is equal to k times of t. Only in these cases you will get the instantaneous speed to be constant. The k can be anything, k can be 5, 6, 7, 2, 3, anything, so it is just a constant. So v instantaneous is equal to k is equal to constant. So what about the instantaneous acceleration? Obviously, because v is constant, so derivative of that constant will be equal to 0. That means there is no acceleration. Quite obvious, because the speed is constant, means its speed is not changing, and because its speed is not changing, the body is not accelerating. It's that simple. So the acceleration here is equal to 0. And make sure you remember the example, that is the case, that is s is some constant multiplied with t. You can take these examples, s is equal to 5 times of t, or s is equal to 2t plus 6, likewise. So s is directly proportional to t over here, the first power of t. Okay, so only in those cases. Graphically, it is just in the form of a straight line equation, if you remember easily. That is y is equal to mx plus c, is where y is dependent and x is independent. And so similarly we have s is equal to k times of t plus c. C is another constant like k. Okay, so s remains in the dependent axis and t remains in the independent axis. Okay, and so we have a straight line where c is the y-intercept, as you can see over there. C is the y-intercept, and the slope that we obtain is nothing but k, because mx, so that is kt, so k is the slope over here. And if the y-intercept is absent, that is c is equal to 0, that is s is equal to only kt, as we had written in the equation, it passes through the origin, that is at 0. So the slope still remains to be equal to k, but it passes through the origin there, right? So this is just a um, graphical representation for better understanding. Now in the second example, second case, we can take as s is equal to some constant times of square of time. Okay, so that was single power of t, this is double power, that is square of time. So again, derivative, if we take the derivative, then k goes outside as a constant, and d square by dt square by dt is equal to 2t, so 2kt. So now instantaneous velocity has some value with respect to time, that means it keeps on changing. Now we can consider the acceleration, which is obtained obviously to be constant. So this is what we deal with. Okay, the instantaneous velocity here is changing when s is equal to square times of t, and the acceleration is remaining constant. This is the frame of reference that we always consider. Yes, this is the constant acceleration frame of reference that we deal with at this level of kinematics. We always come across this. Now you can tell a familiar equation I can give you, which you all must be knowing. This is in the same line as s is equal to kt square. That equation, it is in the same line as you have the one of the equations of motion, right? That is s is equal to ut plus half at t square. So there also s is depending on the square of t. Yes, right there. So s is equal to ut plus half a t square, so t square at the end, that suggests that s is here varying at the square of t. But for problem's sake, we can consider higher powers of t, that is t to the power 3, t to the power 4. We have done such problems before as well in the previous videos. So in such a case, that is the case we have considered, that is s is proportional to square of t. In such a case, the given object is under constant accelerated motion. Okay, we are getting the acceleration, but the acceleration is constant, it is not changing. So because the instantaneous acceleration, but the t to the power 3, t to the power 4 cases, in those problems that we have done, for those cases the acceleration varies. Okay, so we will go back to the numericals. As we know that average speed and average acceleration, okay, is obtained between a certain interval of time, that is from a given t1 time to another time t2. So a person starts from a particular time, or a vehicle starts from a particular time and ends at a particular time, that is from t1 to t2. So the total time taken by the vehicle or the person is t2 minus t1, that is the final time minus the initial time. For example, if it starts from 3 seconds to second time is 10 seconds, so 10 minus 3 is 7. But what about the instantaneous cases? We have learned that instantaneous cases, v instantaneous and acceleration instantaneous at a particular instant of time. So this is interval of time is in case of average speed. In instantaneous cases, it is a particular interval of time. So we can take an example and differentiate between the two, the difference between the two. Okay, so s is given here to be equal to 5t square plus t plus 6 meters. Now we have to calculate the average speed between the time t is equal to 2 seconds to t is equal to 4 seconds, and then we calculate the instantaneous speed at t is equal to 5 seconds. So the first part of the answer that we get, that is the average speed, as you know the formula, that is equal to total distance traveled by the total time taken, or total distance traveled means total change in position, that is the total change in position divided by the total time taken. So the change in position has to be obtained. So what was its position at t is equal to 2 seconds? Now at t is equal to 2 seconds, in the above formula I just have to substitute the value 2 instead of t, that is 5 into t square. I put there 5 into 2 square plus 6, so I get 5 into 4 plus 6, that is equal to 26 meters. So this is the position, okay, at t is equal to 2 seconds. Now similarly, for t is equal to 4 seconds, I just substitute the value of t as 4. Okay, so 5 into 4 square, 5 into 16 plus 6, that is equal to 86. So this is the position at t is equal to 4 seconds. Now I take this as s2, that is the second position, and the first position as s1, that is equal to 26 meters that we had obtained. So s2 in time t2 is 4 seconds, s1 in time t1 is equal to 2 seconds. So v average is equal to delta s by delta t, which is equal to s2 minus s1, that is the change in position, by t2 minus t1, that is the change in time, that is 86 minus 26 by 4 minus 2, that is 60 by 2, which is equal to 30 meters per second, is what we obtained over here as per our equation that has been given, right? So this is the average speed that we have obtained, right? Then we move over to the second part, that is the instantaneous speed. We just have to differentiate it, that is ds by dt, d by dt of s. The equation for s is 5t square plus 6, that is 5 goes outside, so I have taken it in the complete bracket, but it's actually for the first one. So 5 into 2 times of t, I had written dt by dt over there, that is a raw mistake over there I had made. So 5 into 2t, you can check the derivative, 5 into 2t, that is equal to 10t, and I replace at t is equal to 5 seconds, so 10 times of 5, that is equal to 50 meters per second. That is the instantaneous speed over there. So obviously the acceleration as per the equation, as you can see, that s is varying as square of t. Okay, I told you before that the acceleration will obviously remain constant. Now we had obtained for v instantaneous to be value to be equal to 10t. So again differentiating that, we get the value only to be equal to 10 meters per second. You can go through it slowly. So the acceleration is a constant one, that is 10 meters per second. It is completely predictable now. You can predict yourself by looking at the equation whether the acceleration is constant or it is variable, or the velocity is constant or variable. So even if you take the average acceleration between two times, it will still remain the same because the instantaneous acceleration itself is a constant. Okay, so this is what I had to discuss about the physical significance, as well as the problems, how you deal with them related to average and instantaneous cases. Average always takes two time intervals and instantaneous is only focused on an instant of time. So this was all for today. In the next video we will be proceeding further into the chapter, some more interesting things related to it. Till next time, goodbye. Thank you for your patience. Bye.